This is section 8.1, day 1. We're going to start with sequences. A sequence is a function whose domain is a set of positive integers. A sub 1, a sub 2, a sub 3, all the way to a sub n. A sub n is called the nth term, and we denote the sequence by, and we use the curly brackets with the function or the expression inside of the curly brackets. Example, write the first 5 terms of the sequence, where a sub n is 3 to the n. So I have 3 to the 1, 3 to the 2, 3 to the 3, 3 to the 4, and 3 to the 5th. Now we're not going to leave it like that, but we have 3, 9, 27, 81, and 243. In the second one, a sub n is 2 over n factorial. Recall that 4 factorial is equal to 1 times 2 times 3 times 4, which is 1 times 2 is 2, 2 times 3 is 6, so we have 6 times 4, which is 24. In the sequence, we have 2 over 1 factorial, 2 over 2 factorial, and so on. 2 over 3 factorial, 2 over 4 factorial, and then 2 over 5 factorial, which it can be written as, well, 1 factorial is just 1, so we have 2 over 1, which is 2. 2 over 2 factorial, that's 1 times 2, that's just 2. So 2 over 2 is 1. And then if you want to know what 3 factorial is, you can just take 2 factorial times 3, that's 6. That reduces to 1/3. 6 times 4, that's 24. So 2 over 24 is 1/12. And finally, if this is 24, take that times 5, because it's 4 factorial times 5. That gives you 5 factorial. 5 times 4 is 20, 10 looks like 120. So 2 over 120 is 1/60th. An arithmetic sequence is each term is found by adding to the previous term. The value added is called the common difference. Now this is an arithmetic sequence. A sequence is, well, you take let's redo this. Let's talk about an arithmetic sequence. To find an arithmetic sequence, or the definition is each term is found by adding to the previous term. The value added is called the common difference, and the explicit formula is written as a sub n equals a plus n minus 1 times that common difference, which is d. Well, let's look at a simple one. How about we start out with 3 and add, well, let's just take the first one. This is actually an arithmetic sequence. We're going to keep adding 5, so we have 8, 13, 18, and so on. So we're adding 5. That's the common difference. So d ends up being 5. But we're going to base it off of the first one, a sub 1. So when on the first one, we want to take a sub 1, and we don't really want to add 5 at all, not when n is 1. So we have 3 plus the nth term minus 1, and then times the common difference, which is 5. So we don't want to add 5 on the first one. So when we plug 1 in, we're going to add nothing, because 1 minus 1 gives us 0. So this is the first term. Here's the second term. Now we want to actually add the 5 on. So we have the 3 plus, plug 2 in here. 2 minus 1 is 1, so we'll add 1 5. Then on the third term, we want to take the original and we want to add on another 5. We want to add on 10. So when we plug 3 in here, we have 3 minus 1 now, which is 2, and 2 times 5 is 10. So we'll take the original and we'll add 10. Well, then for the fourth term, we want to add 15. So we want to add 1 less than what we're on. We want to add that many 5s. So hopefully that gives you a little understanding of this formula. A geometric sequence, each term is found by multiplying to the previous term. The value multiplied is called the common ratio. And that formula is a sub n equals a sub 1. We always base it off in the first term. And it's a similar concept, except we're going to multiply by 1 less than the term that we're on. And we'll take the next one, for example, 5, negative 15, 45, negative 135. The common ratio is negative 15 divided by 5, or 45 divided by negative 15, but the point is they're all negative 3, so the common ratio is negative 3. So we're starting with 5, and on the first term we don't want to multiply by anything. That's the first term. So if I plug 1 in for n, we get that common ratio, which is -3 to the 0. So that first term, which is 5, is going to get multiplied times 1, which is just itself. Then if we have the second term, then we plug 2 in for n, we're going to multiply by -3 to the 2 minus 1, which is -3, and that's what we want to do on the second term. We want to multiply by -3. Well, then when n is 3, I want to multiply by 9, and that'll be -3. We're on the third term. 3 minus 1, that'd be -3 squared. That's 9. So hopefully that helps you understand the formula that you need to know, which is sitting right there for a geometric sequence. Well, we've already kind of covered A and B, but let's look at what's happening here. We're adding 5, adding 5, adding 5, and keep on going. So A sub n, it says write an expression for the nth term, equals A sub 1, which is 3, plus n minus 1 times the common difference. So we have 8 minus 3 is 5, 13 minus 8 is 5, 18 minus 13 is 5. Those are all 5s. So the common difference is 5. Now the book may distribute, or if you get a multiple choice, might distribute, and the answer could also be 5n minus 2. This one, like we said earlier, is multiplying by -3 to each term to get to the next. So A sub n equals the first term, 5, times the common ratio to the n minus 1, and there's not really much we can do with this. These are all perfect squares, so A sub n equals n squared. This one is a lot harder to see, but once you do a few of these, you get the hang of it. This one is a little harder to see, but it is 3 to the n, and then add 1. So this is 3 plus 1. This is 9 plus 1. This is 27 plus 1. This is 81 plus 1. So A sub n equals 3 to the n plus 1. Lab on investigating sequence. Let the sequence be a sequence of real numbers, the possibilities. If we take the limit as x approaches infinity every time, A sub n might approach infinity. Then the sequence diverges to infinity. So it diverges. If the limit is -infinity, then the sequence diverges to -infinity, of course. However, if we take the limit as n approaches infinity and it equals some value, a finite real number, then we say that it converges to C. If the limit as n approaches infinity of A sub n oscillates between two numbers, then we say the sequence diverges by oscillation. In parametric mode on the TI-83s and TI-89s, etc., you want to, if you put your mode of the calculator in parametric, to graph these sequences, you let x sub 1 equal t, and you let y sub 1 equal the actual function. The window, for example, the t can be from 1 to 20, but you got to make your step equal to 1 because we're plugging in 1, and then we're plugging in 2, and then we're plugging in 3. You don't want to plug in 1.1, 1.2, 1.3. That doesn't make any sense for sequences. The x needs to be from -1 to 20, and the y needs to be -1 to 5. In the mode, also, you'll want to put your calculator into dot, not connected. Press graph and then trace to see the terms of the sequence. Be sure that, yeah, here it is. You're in dot mode, so the dots won't be connected. So if you have dots for the sequence, you want to see those dots. You don't want to see this curve, even though it may not make a huge difference. Use your graphing calculator to determine the following sequences converge, whether the following sequences converge or diverge. Look at both both the graph of the sequence and the table of y values as n increases. Here are the answers. We're going to do this in class, but if you're watching these videos, you can compare your answers to these. If a sequence has a finite limit as n approaches infinity, we say that the sequence converges. If a sequence does not have a finite limit as n approaches infinity, then it diverges. Determine whether the following sequences converge or diverge. Well, so we're going to take the limit as n approaches infinity of n over n plus 1. Well, as n approaches infinity, it's no different than saying the ending behavior. And when the powers match, we take the coefficients, and so this one converges to 1. Let's look at letter B. We have the limit as n approaches infinity of 1 over 2 to the n, which is just simply 1 over infinity. 2 to the infinity is just infinity. So this one actually converges to 0. In letter C, we have the limit as n approaches infinity of 3 plus the limit as n approaches infinity of negative 1 to the n. Well, the first part is 3. And then we have plus, well, if n is 1, it'll be negative 1. If n is 2, it'll be positive 1. And then if n is 3, it'll be negative 1. So we have 3 plus negative 1 or 1. So this will oscillate. 3 minus 1 is 2. And then you add 1, that is 3. And then you minus 1, it's 2. And then you add 1, it's 3. So this one will oscillate between 2 and 3, 2 and 3. So this one diverges by oscillation. In letter D, we have the limit as n approaches infinity of n over 1 minus 2 to the n. This is ending behavior. So we have just 1 over negative 2. So this one converges to negative 1/2. In letter E, we have the limit as n approaches infinity of infinity over infinity. So we can use L'Hopital's. We have the limit as n approaches infinity of the derivative of natural log of n is 1 over n, and the derivative of n is 1. This is 0. So this one converges to 0. In letter F, let's look at a specific example to figure this one out. If we had a sub 6, that would be equal to 6 factorial over 8 factorial, which we could write as 6 factorial on top over 6 factorial times 7 and then times 8. And the 6 factorials would cancel out. Let's look at that with just n's. Limit as n approaches infinity of, we would have n factorial over, we could write that as n factorial on the bottom, but then times n plus 1, and then times n plus 2. So the n factorials would cancel out. We have the limit as n approaches infinity of 1 over n plus 1 times n plus 2, and that's 1 over infinity, which is 0. So this one converges to 0. In letter G, let's look at another value for n. Let's say 6. This one would be 6 factorial over 5 factorial. You could write this as 5 factorial times 6 over 5 factorial. Those would cancel out and you'd have 6. Let's look at this with n. We'd have limit as n approaches infinity. This would be n minus 1 factorial times the nth term, because remember n would be 6 in this case, all over n minus 1 factorial. If n was 6, we'd have 5 factorial down here. So these are going to cancel out, and we're left with the limit as n approaches infinity of just n, which is infinity. So this one diverges to infinity.